In a modern American hangar, a brand new $1 million light aircraft rolls onto the tarmac. It features a carbon fiber airframe, satellite weather screens, a digital autopilot, and a ballistic parachute. But unlatch the cowling, and you will find an air-cooled, push-rod piston engine that was fundamentally designed when Dwight D. Eisenhower was president. This is a Lycoming. For decades, the American aviation market has tried to replace it. Car engines advanced, turbines took over the commercial skies, and electric motors emerged. Yet the horizontally opposed Lycoming remains the undisputed heartbeat of general aviation. It did not survive simply because it was flawless. It survived because an inescapable web of product liability lawsuits, extreme FAA certification costs, and a systemic reliance on 100-octane leaded fuel locked the industry in the past. Mechanics learned its every rhythm. Flight schools depended on its mechanical predictability. New competitors found the regulatory wall too expensive to climb. But the real story of Lycoming is not only the story of an old engine in a new airplane. It is the story of how an entire American industry became trapped by its own demand for perfection. Every week, we tell the stories of American engines, factories, machines, and industrial names that once taught the country what power sounded like, and what happened when the market moved on. Subscribe if that history matters to you. The story begins not with nostalgia, but with a specific place, in Williamsport, Pennsylvania in 1929. The story begins in Williamsport, Pennsylvania, long before anyone in America thought about putting an airplane in a suburban garage. In the late 19th and early 20th centuries, Lycoming was not an aviation company. It was a metalworking manufacturer. It built sewing machines. It built bicycles. By 1907, it had transitioned into automobile engines, pouring iron for a rapidly expanding American automotive industry. Throughout the Roaring '20s, Lycoming engines powered some of the most prestigious luxury cars in the country, including Auburn, Cord, and Duesenberg. But automotive empires are fragile. When the Great Depression hit, the market for luxury automobiles evaporated. To survive, Lycoming had to look up. In 1929, the company introduced its first aviation engine, the R680. It was a 9-cylinder radial engine. A radial engine, a piston aircraft engine with cylinders arranged in a circle around the crankshaft, was the undisputed standard of early American aviation. It produced 200 horsepower, sounded like a thunderstorm, and leaked oil on the hangar floor. The R680 was highly successful, powering biplanes, early airliners, and military trainers. Throughout World War II, Lycoming's foundries ran constantly, churning out radials and specialized components to support the American war effort. But as the war ended in 1945, the American aviation market faced a massive structural shift. Hundreds of thousands of military pilots were returning home. The GI Bill offered flight training. Manufacturers like Piper, Cessna, and Aeronca believed that the post-war American middle class would embrace personal aviation the way they had embraced the automobile. In 1946 alone, the American general aviation industry produced over 30,000 light aircraft. It was a boom unlike anything the world had ever seen. But a light two-seat airplane like a Piper Cub could not use a heavy radial engine. A radial engine was too wide, creating massive aerodynamic drag on a small airframe. It was too complex, requiring specialized maintenance that local mechanics could not easily provide. And it was simply too heavy. The alternative at the time was the inline engine, similar to what powered a car. But inline engines usually required liquid cooling. A liquid-cooled engine relies on a radiator, a water pump, hoses, and liquid coolant to pull heat away from the block. In an automobile, a coolant leak means pulling over to the side of the highway and calling a tow truck. In an airplane, a coolant leak over a dense Pennsylvania forest or a sprawling Midwest farm field means an emergency landing and a potential fatality. Every hose was a liability. Every water pump was a failure point. The American general aviation market did not just need an engine. It needed a new architecture of trust. It needed a machine that was cheap enough for a returning veteran to buy, light enough to bolt to the nose of a fabric-covered airplane, and mechanically invincible. Lycoming's answer was to lay the engine flat and let the wind do the work. They doubled down on the horizontally opposed air-cooled piston engine. A horizontally opposed engine, also known as a flat engine, is a design where the cylinders are divided into two banks, laying flat and pointing away from each other. This layout inherently balances the engine, reducing the brutal vibration that can tear an airframe apart. More importantly, it dramatically lowers the engine's profile, allowing it to fit inside a tight aerodynamic cowling at the front of a small airplane. An air-cooled engine is an engine that relies entirely on the slipstream of the propeller and the forward motion of the aircraft to carry away heat, using metal fins cast directly into the cylinder heads. There is no radiator. There is no water pump. There are no coolant hoses to burst. If the propeller is turning and the plane is moving, the engine is cooling itself. Lycoming had experimented with this architecture before the war, introducing the O-145 in 1938. The O stood for opposed, and 145 was its displacement. The total volume swept by the pistons inside the cylinders, measuring 145 cubic inches. It produced just 55 to 65 horsepower, but it proved that the flat-four layout could work. By the late 1940s, as the post-war boom settled into a steady long-term industry, Lycoming scaled up the design. They introduced the O-235, a four-cylinder engine producing over 100 horsepower. It was a block of aluminum and steel that looked rugged, almost agricultural. This engine did not reach Americans through automotive dealerships. It reached them through a rapidly growing network of local flight schools, grass strip airports, and small-town maintenance hangars. In these spaces, mechanics known as A&Ps, airframe and power plant mechanics, certified by the federal government, began to learn the Lycoming architecture. For a mechanic in a freezing hangar in Ohio or a humid flight school in Florida, the Lycoming flat-four was a revelation in serviceability. The engine was modular. The cylinders were not cast into a single immovable block. Instead, each cylinder was a separate jug that bolted directly to the central crankcase. If one cylinder lost compression, a mechanic did not have to remove the entire engine from the airplane. They could unbolt that single cylinder, inspect the piston, lap the valves, and bolt it back on. This was the beginning of a vast American service network. Lycoming was no longer just a foundry in Williamsport. It was becoming a shared language among thousands of mechanics who kept oil-stained service manuals on their workbenches. The company had figured out how to build a machine that could survive the vibration, the heat, and the mechanical abuse of student pilots learning how to fly. The architecture was set, but architecture alone did not build an empire. Lycoming still needed to prove that its iron could outlast the sky it flew in. In 1953, Lycoming introduced the O-320, a four-cylinder engine displacing 320 cubic inches and producing 150 horsepower. 2 years later, in 1955, they scaled the architecture up to create the O-360, displacing 360 cubic inches and producing 180 horsepower. These were not simply new product lines. They became the inescapable foundation of American light aviation. To understand why these specific engines conquered the sky, it is necessary to understand how the American aviation market diverged from the American automotive market. Throughout the 1950s and 1960s, Detroit was obsessed with making V8 engines smoother, higher revving, and increasingly complex. Lycoming went the opposite direction. They realized that in the air, complexity is not a luxury. Complexity is a liability. The Lycoming flat-four was an exercise in brutal, uncompromising simplicity. First, these engines were direct drive, a mechanical layout where the propeller is bolted directly to a flange on the front of the crankshaft, with no transmission or reduction gears in between. In a geared engine, a gearbox allows the engine to spin fast while keeping the propeller slow, but gearboxes add weight, require specialized lubrication, and introduce a catastrophic point of failure. With a direct drive Lycoming, if the crankshaft was turning at 2,700 revolutions per minute, the propeller was turning at exactly 2,700 revolutions per minute. There was nothing between the pistons and the thrust but a solid piece of forged steel. Because it was direct drive, the engine had to operate at a very low redline, the maximum safe rotational speed of the engine. A car engine might scream at 6,000 RPM, but a Lycoming O-360 typically hit its redline at just 2,700 RPM. This was necessary to keep the tips of the spinning propeller from breaking the speed of sound, which would destroy aerodynamic efficiency and tear the prop apart. To make 180 horsepower at such a low speed, the engine needed massive displacement. A 360 cubic inch four-cylinder engine is roughly 5.9 liters. That means the bore, the diameter of the cylinder, was over 5 inches across. The pistons were the size of large coffee cans. Every time the engine fired, it produced a massive low-frequency pulse of torque, the twisting force that physically dragged the airplane through the air. Inside the block, Lycoming stubbornly stuck to an overhead valve layout, a design where a single camshaft sits deep inside the engine case, pushing long metal push rods that actuate the valves in the cylinder head above the combustion chamber. While the automotive world slowly marched toward overhead cams and complex timing chains, the Lycoming pushrod system was heavy, slow-moving, and nearly invincible. For an A&P mechanic in a drafty sheet metal hangar in Kansas, it meant an engine that could be timed, adjusted, and diagnosed with basic hand tools and a set of feeler gauges. But the true stroke of genius in the Lycoming architecture, and the reason pilots trusted it with their lives, was how it generated its spark. These engines relied on dual magnetos. A magneto is an engine-driven electrical generator that uses magnets and copper coils to create high-voltage pulses for the spark plugs, operating completely independently of the aircraft's battery. Furthermore, the engine had two of them, each firing its own set of spark plugs in every cylinder. Modern cars rely on an alternator and a battery to run the computer and the ignition system. If the battery dies, the engine dies. In an airplane powered by a Lycoming O360, a pilot could experience a total electrical failure. The alternator could fail, the battery could drain completely, the radio could go silent, and the entire instrument panel could go pitch black in the middle of the night. But because the dual magnetos were physically driven by the rotation of the engine's internal gears, the spark plugs would keep firing. The engine would keep running until the fuel tanks ran bone dry. In the terrifying quiet of a total electrical failure at 5,000 feet, the mechanical thumping of a Lycoming engine was the sound of survival. Even the fuel systems were kept deliberately primitive. Most models relied on a simple updraft carburetor, a mechanical bowl that uses the suction of the engine to draw fuel and air together before it enters the intake manifold. When Lycoming did introduce mechanical fuel injection, a system that squirts fuel directly toward the intake ports, it was entirely mechanical. There were no computers, no electronic sensors, and no software mapping. This absolute dedication to mechanical predictability made Lycoming the engine of choice for the companies aggressively fighting to put America in the air. Piper Aircraft built its legendary Cherokee line around the Lycoming O320 and O360, and when Cessna needed an engine for its training aircraft, they eventually turned to Williamsport. In 1968, Cessna switched the engine in the Cessna 172 to the Lycoming O320. The Cessna 172 would go on to become the most produced aircraft in the history of the world, with over 44,000 units built. Suddenly, Lycoming was no longer just a participant in the market. It was the market. To capture the heavier end of the industry, Lycoming simply took their proven four-cylinder architecture and added two more cylinders, creating the O540 and IO540 series. These were massive six-cylinder engines displacing 140 cubic inches and producing up to 300 horsepower. The IO540 powered heavy backcountry bush planes hauling cargo in Alaska, high-performance cross-country cruisers, and twin-engine business aircraft. Crucially, the internal parts were largely interchangeable with the four-cylinder engines. A mechanic who knew how to rebuild an O320 automatically knew how to rebuild an IO540. By the end of the 1960s, Lycoming had built an iron wall around the general aviation market. They had created a machine that perfectly answered the demands of post-war American flight. The engine had become the undeniable heartbeat of American general aviation. But finding the top of the market is dangerous because it is exactly where the rules begin to change. By the late 1970s, the American general aviation industry was not just thriving. It was operating at a scale that the world would never see again. In 1978, American manufacturers built over 17,000 light aircraft in a single year. In 1979, the production numbers climbed even higher, and the vast majority of those airplanes were pulled into the sky by an air-cooled, horizontally opposed engine cast machined and assembled in Williamsport, Pennsylvania. Lycoming had moved from being a product to becoming an American industrial standard. To understand its absolute dominance, you had to look down at the thousands of municipal airports, grass strips, and flight schools that dotted the American landscape. In Florida, vast flight academies like Embry-Riddle Aeronautical University ran fleets of Piper Arrows and Cessna 172s from dawn until dusk, training the next generation of commercial pilots. In the backcountry of Alaska, cargo pilots trusted the heavy 300-horsepower Lycoming IO 540 in their Cessna 206 stationaires to haul supplies over unforgiving, frozen terrain. Across the Midwest, crop dusters, pipeline patrol pilots, and weekend hobbyists depended on the engine's absolute refusal to quit. The Williamsport factory itself was a cathedral of American manufacturing. Inside, the foundry poured aluminum cylinder heads and heavy steel barrels. Machinists milled aluminum crankcases with tolerances measured in the 10,000ths of an inch. The assembly line was a synchronized ballet of push rods, camshafts, and massive pistons. They were not building disposable consumer goods. They were building mechanical life support systems. But the empire was no longer just about the factory. It was about the massive service network that had grown around the engine block. Every American airport with a maintenance hangar had an A&P mechanic who knew the Lycoming architecture by heart. The engine was so ubiquitous that it became the baseline curriculum for aviation mechanics across the country. In vocational schools and community colleges, young mechanics learned how to safety wire a propeller, time a magneto, and measure the bore of a cylinder using Lycoming service manuals stained with aviation oil. A mechanic did not need to guess how a Lycoming worked. They knew that a 2,000-hour TBO, time between overhaul, the manufacturer's recommended operational lifespan of the engine before it required a complete teardown and rebuild, was not just a suggestion. It was an industrial rhythm. At exactly 2,000 flight hours, the engine was pulled from the airframe, split in half on a heavy steel engine stand, and meticulously rebuilt with fresh bearings, rings, and gaskets, before being bolted right back onto the firewall to fly another 2,000 hours. In an America where a single engine failure meant falling from the sky, power was not an abstraction. It was iron, fuel, mechanical empathy, and an absolute trust in a machine shop in Pennsylvania. The cultural presence of Lycoming was best understood through its sound. A Saturday morning at a municipal airport in California or Texas was defined by a specific mechanical ritual. A pilot would walk out to a two-seat Cessna 152, visually inspect the aircraft, drain a small cup of fuel from the wings to check for water, and climb into the cabin. They would push in the red mixture knob, hit the primer, crack the throttle, and turn the ignition key. The starter would whine heavily against the flywheel, and then the Lycoming O235 would catch. It did not hum smoothly like a modern automobile engine. It coughed, shook the entire airframe violently for a split second, and then settled into a rhythmic, low-frequency thump. It was the distinct sound of a mechanical heart waking up. And then there was the fuel. This empire ran on a very specific type of energy, 100 LL, or 100-octane low-lead aviation gasoline. While the American automotive industry was being forced by the Environmental Protection Agency to transition to unleaded fuel and catalytic converters throughout the 1970s, aviation was granted an exception. The massive pistons and high cylinder pressures of aircraft engines required lead to prevent detonation. A catastrophic, premature explosion of the fuel-air mixture that could melt a piston in midair. The blue-dyed 100 LL fuel became the lifeblood of the Lycoming empire, smelling sharply of solvent and leaving a grayish-white residue on the exhaust pipes of every plane on the ramp. Lycoming had successfully powered the golden age of American flight. The engines were everywhere, supported by an unbroken chain of fuel trucks, flight schools, parts counters, and mechanics. To understand the sheer scale of the Lycoming empire at its peak, you had to look at the sky over the American West. As general aviation matured, pilots wanted to fly higher, over storm systems and massive mountain ranges like the Rockies. To do this, the engine had to breathe in thin air. Lycoming's answer was the TIO 540. The T stood for turbocharged. A turbocharger, a device driven by hot exhaust gases that forces compressed, dense air into the engine's intake. allowed the flat six-piston engine to maintain its sea-level horsepower all the way up to 20,000 feet. Suddenly, American businessmen, doctors, and regional cargo haulers were flying pressurized, twin-engine aircraft like the Piper Navajo and the Cessna 310 at altitudes previously reserved for military planes and commercial airliners. Yet under the cowling, it was still the same basic, air-cooled, pushrod architecture. Lycoming had figured out how to stretch a 1950s mechanical concept to the absolute limits of atmospheric physics. By the late 1970s, the active fleet of general aviation aircraft in the United States was approaching 200,000 planes. The vast majority of them were powered by horizontally opposed engines, and Lycoming held a dominant share of that iron. The brand had become so deeply embedded in American aviation that it operated less like a competing business and more like a public utility. This dominance was cemented by the parts counter. In the automotive world, if a car broke down in a remote town, finding parts for a rare engine might take weeks. But in the aviation world, uniformity was safety. A pilot could land a sputtering airplane on a remote dirt strip in Idaho, a private ranch in Montana, or a massive concrete ramp at Van Nuys Airport in California, and know with absolute certainty that the local maintenance shop had the gaskets, the piston rings, and the exact knowledge required to pull a cylinder off a Lycoming 0360. The service network had become an invisible infrastructure spanning the entire continent. Distributors stocked Lycoming parts in every major region. Trade magazines were filled with advertisements from specialty machine shops in places like Tulsa and Dallas that did nothing but regrind Lycoming camshafts or overhaul Lycoming carburetors. This ecosystem created a unique American ownership culture. A Lycoming engine was not a disposable consumer product. It was a generational asset. In a car, an engine with 100,000 miles was nearing the end of its life, and the vehicle would eventually be traded in or sent to a junkyard. But in a Cessna or a Piper, the engine was perpetually rebuilt. Every hour of its life, every drop of oil added, and every mechanical adjustment was meticulously recorded in a bound paper logbook signed by a certified mechanic. When an engine reached its factory-recommended overhaul limit, it was not thrown away. The block was split. The steel internals were subjected to magnetic particle inspection, a process that uses magnetic fields and iron powder to detect microscopic cracks in the metal. And the machine was rebuilt to factory-new tolerances. A single Lycoming engine block cast in Williamsport in 1968 might be overhauled in 1975, rebuilt again in 1984, and be flying a completely different owner across the country in 1995. By 1979, the industry seemed invincible. Flight schools were packed. The Williamsport factory was shipping thousands of engines a year. The American middle class had embraced personal aviation, and Lycoming had provided the unyielding, cast-iron heartbeat for that movement. The engines had proven that they could survive student pilots, freezing altitudes, searing desert heat, and decades of continuous use. The sky belonged to Lycoming, but the threat to its empire would not come from a better piece of engineering. It would come from a courtroom, a rule book, and a fuel pump. The first crack in the American general aviation empire did not happen on a runway, and it did not happen on the factory floor in Williamsport. It happened in an American courtroom. By the early 1980s, the legal environment surrounding American manufacturing had fundamentally changed. The country entered a severe product liability crisis. In the aviation sector, the rules of liability meant that if a 30-year-old airplane crashed, the manufacturers of the airframe, the engine, and the components could be sued, regardless of how many times the plane had been sold, how it had been maintained, or whether pilot error was the primary cause of the accident. Because Lycoming and the major airframe builders had the deepest pockets, they became the default targets for massive lawsuits. The mathematical reality of building an aircraft engine shifted. The cost of liability insurance skyrocketed, and manufacturers had to bake that insurance premium into the price of every new engine and every replacement part they sold. The market reaction was violent and immediate. In 1978, the American industry had built over 17,000 light aircraft. By the mid-1980s, that number had plummeted by more than 80%. The cost of a new airplane became mathematically unjustifiable for the average middle-class buyer. Then came the ultimate shock to the system. In 1986, Cessna, the largest producer of light aircraft in the world and one of Lycoming's most vital partners, did the unthinkable. Facing insurmountable liability costs, Cessna entirely suspended the production of piston-powered aircraft. Piper Aircraft, another massive buyer of Lycoming engines, was pushed into bankruptcy and reorganization. The great American assembly lines that had been churning out thousands of planes a year suddenly went quiet. Lycoming found itself trapped in a bizarre industrial purgatory. Their biggest customers were no longer buying new engines in volume. Yet because there were still hundreds of thousands of active Lycoming engines flying over American cities, farms, and highways, the company was legally and financially bound to support them. They became a supplier for a legacy fleet, churning out replacement cylinders, crankshafts, and overhaul kits to keep the existing planes in the air. This legal and economic trap created a profound technological freeze. In the 1980s and 1990s, the American automotive industry was undergoing a massive technological revolution. Driven by federal emission standards and fuel economy pressure, car engines rapidly adopted electronic fuel injection, overhead camshafts, liquid cooling, and computer-controlled ignition systems. Engines became lighter, more efficient, and incredibly reliable. But aviation is governed by the Federal Aviation Administration, and the FAA requires an engine to possess a type certificate, a grueling federal approval process proving that a specific engine design can operate safely under extreme, sustained conditions without failing. Obtaining a new FAA type certificate for a clean sheet engine design costs tens of millions of dollars. For Lycoming, spending millions to develop a modern, liquid-cooled, electronically controlled engine made absolutely no financial sense when the airframe manufacturers had stopped building new planes. Any change to the existing, proven engine, even something as simple as redesigning a cylinder head for better airflow or updating the ignition system, required expensive recertification and opened the company up to fresh legal liability if the new part failed. So Lycoming changed almost nothing. The architecture was locked in place. An American pilot in 1992 might drive to the local airport in a car equipped with computerized engine mapping and an advanced emission system. But when they walked out to the tarmac and rented a Cessna or a Piper, they were stepping behind an engine that still used heavy steel pushrods, mechanical updraft carburetors, and dual magnetos that generated their own spark, independent of a battery. The technology gap between the highway and the sky, which had once favored aviation, inverted entirely. This technological stagnation should have killed the company. In any normal free market, a competitor would have seen the outdated technology, built a modern, efficient, computer-controlled aviation engine, and taken over the industry. Several companies tried. Throughout the 1990s and 2000s, startups attempted to introduce automotive-derived liquid-cooled engines, advanced rotaries, and lightweight V8s into the general aviation market. Some of these engines were smoother, quieter, and burned significantly less fuel than a Lycoming 0360. But they all hit the same impenetrable wall. First, they had to spend millions navigating the FAA certification process. Then they had to convince conservative pilots to trust an unproven design with their lives. And finally, they collided with Force 2 of the American engine market, the service network. If a pilot flying a new, experimental, liquid-cooled engine had a mechanical issue in a small town in Nebraska, the local A&P mechanic would open the cowling, look at the radiator, the coolant hoses, and the electronic engine control unit, and refuse to touch it. There were no service manuals on the shelf. There were no spare parts in the bin. But if that same pilot landed with a Lycoming, the mechanic could diagnose a rough magneto or a stuck valve in 20 minutes, order the exact part from a distributor, and have the plane flying the next afternoon. The Lycoming engine was no longer just a piece of machinery. It was an institutional standard. It survived the collapse of the new plane market because it had a monopoly on the knowledge of the American aviation mechanic. The engine was completely safe from the threat of new competitors, but it was not safe from the changing chemistry of American fuel. To understand the final inescapable trap that closed around the Lycoming empire, you have to look at the fuel pump at any local American airport. The pump handle is often marked with a bright blue placard, dispensing a fluid-dyed light blue, smelling sharply of solvent. This is 100 LL, 100-octane low-lead aviation gasoline. By the late 1990s and into the 2000s, the rest of the American transportation network had fundamentally moved on. The automotive industry had abandoned leaded gasoline entirely, forced by the Environmental Protection Agency to adopt unleaded fuels and catalytic converters to clean up the air. But general aviation was granted a federal exemption. The exemption existed because of the brutal physics inside a Lycoming cylinder. The massive 5-inch pistons and high cylinder pressures of an air-cooled aircraft engine created immense heat. If you ran standard automotive unleaded fuel in a high-compression aircraft engine like the Lycoming IO540, the heat and pressure would cause detonation, a catastrophic condition where the fuel-air mixture explodes violently and prematurely, rather than burning smoothly. Detonation acts like a sledgehammer against the top of the piston. Within minutes, it can melt a hole straight through the aluminum, destroying the engine in midair. Tetraethyl lead was the chemical additive that prevented detonation. It stabilized the fuel. It was the magic ingredient that allowed 1950s engine architecture to survive into the 21st century. But relying on lead became a systemic vulnerability. 100 LLL is a specialty blend. Because the volume of general aviation fuel is minuscule compared to automotive gasoline or commercial Jet A, the kerosene-based fuel used by turbine engines and jet airliners, very few American refineries were willing to produce it. The supply chain became fragile. A disruption at a single chemical plant could send aviation fuel prices skyrocketing across the country, changing the math for every flight school and private owner in America. Worse, the EPA and local governments began to aggressively target the fuel. In places like California, municipal airports faced intense political pressure and local bans on selling leaded aviation gas due to the toxic lead particulates settling over nearby neighborhoods. The American Engine Market Force of Regulation and Emissions, Force 3, was closing in. But Lycoming, now owned by the massive industrial conglomerate Textron, was paralyzed. They could not easily redesign their high-performance engines to run on lower-octane unleaded fuel without drastically reducing horsepower. And reducing horsepower meant the airplanes those engines powered would no longer meet their original FAA-certified flight performance metrics. The industry desperately searched for an alternative. European companies began developing aerodiesels, aircraft engines designed to burn Jet A fuel, which is universally available, lid-free, and highly efficient. But a diesel engine relies on extreme compression ratios, requiring heavy iron or heavily reinforced aluminum blocks. They were expensive to buy, heavy to install, and required completely different service intervals. More importantly, the American service network rejected them. The aviation maintenance ecosystem in the United States had spent half a century learning the Lycoming Flat 4 and Flat 6. An A&P mechanic knew exactly how a Lycoming sounded when a valve was sticking. They knew the specific torque specs for the cylinder-based nuts. They knew how to overhaul a magneto. When faced with a modern, liquid-cooled, computer-controlled aerodiesel, many American maintenance shops simply refused to work on them. They did not have the diagnostic software, they did not have the parts bins, and they did not have the legal desire to take on the liability of an unfamiliar machine. So the Lycoming engine stayed bolted to the firewall. It survived not by innovating, but by being too legally and mechanically entrenched to replace. This created a strange industrial twilight. The Williamsport factory was still operating. Lycoming was still casting blocks, machining cylinders, and shipping parts. But it was no longer a company powering a massive, expanding American frontier. It had become a supplier for a closed ecosystem. The vast majority of its business shifted from powering new airplanes to providing overhaul parts and factory rebuilt engines for the aging legacy fleet. Even the human infrastructure began to crack. The generation of mechanics who had grown up adjusting mechanical carburetors and timing dual magnetos began to retire. Aviation maintenance programs struggled to attract young technicians who were increasingly drawn to the software-driven world of modern automotive repair or commercial turbine aviation. The knowledge of how to keep a 1950s pushrod engine alive was slowly aging out of the American workforce. The engine was surrounded by a world that was moving away from it. Electric propulsion startups began testing battery-powered trainers. High-end modern aircraft like the Cirrus SR-22 featured massive digital screens, synthetic vision, and parachute systems. Yet they were still forced to rely on heavy, large displacement, air-cooled piston engines, burning a toxic fuel that the rest of the world had outlawed. The machine was caught in a time capsule, held there by the weight of the federal rulebook, the fear of the courtroom, and the limitations of the fuel pump. The engine still ran. The fuel became a target. The lawsuits remained. The certification rules tightened. The old mechanics retired. The factory line slowed. The technology stayed frozen. The badge survived. The golden age was gone. But what was left was no longer an industry of mass production. It was an American culture of absolute mechanical preservation. The Lycoming engine empire did not end in bankruptcy, and the factory doors in Williamsport, Pennsylvania did not close. Unlike the great radial engine makers that were entirely swept away by the jet age, or the massive Detroit automotive divisions that were dissolved into corporate memory, Lycoming survived. Today it remains a heavily guarded subsidiary of the industrial conglomerate Textron. If you possess the capital, you can still call a distributor and order a brand new zero-hour Lycoming 0360 or IO 540. But survival in the American aviation market came with a strange, paradoxical condition. The Williamsport plant is a modern manufacturing facility utilizing advanced computer numerical control machining and high-tech quality assurance. Yet the machines they are cutting out of raw aluminum and steel are fundamentally 1950s architecture. They are building brand new antiques, perfectly machined time capsules designed to satisfy an aviation market that cannot legally or financially afford to change. The true legacy of Lycoming, however, does not live in corporate boardrooms or modern assembly lines. It lives in the American hangar. Every summer at the Experimental Aircraft Association's AirVenture Fly-In at Oshkosh, Wisconsin, thousands of small airplanes descend onto the grass strips and concrete runways. When you stand on the flight line as the morning dew burns off, the air is thick with the smell of 100 LL aviation fuel and the overlapping rhythmic thumping of thousands of air-cooled flat fours and flat sixes. It is the sound of an entire subculture that refuses to let the internal combustion engine die. Within this culture, the American A&P mechanic holds a position of profound industrial respect. The aviation mechanic did not become a parts replacer plugging a diagnostic laptop into a sealed system. Because the Lycoming engine was designed to be endlessly rebuilt, the knowledge of how to safety wire a turnbuckle, lap a valve, and time a dual magneto was passed down like a sacred trade. Across the country, in vocational schools and local flight academies, oil-stained Lycoming service manuals are still spread across workbenches. The engine created a multi-generational workforce that understands the raw physics of metal, heat, and friction better than almost anyone else in the modern American economy. There is also a surprising footnote to the Lycoming story. While the certified aviation market remained locked in a regulatory deep freeze, a parallel market emerged: the experimental home-built aircraft movement. Under FAA rules, if an individual builds the majority of an aircraft themselves for education and recreation, they are not bound by the same crippling certification rules as Cessna or Piper. In this experimental space, companies began building Lycoming clone engines. Without the multi-million-dollar burden of FAA-type certificates, homebuilders took the rugged, proven Lycoming block and finally did what the factory could not. They stripped off the heavy, mid-century dual magnetos and installed modern, solid-state electronic ignition systems. They threw away the mechanical updraft carburetors and bolted on advanced, computer-controlled electronic fuel injection. They proved that the foundational iron of the Lycoming Flat 4 was brilliant. It was only the regulatory environment that had held it back. In the experimental world, the 1950s engines suddenly met the 21st century, becoming smoother, more efficient, and dramatically more powerful. This is not nostalgia. A Lycoming 0360 sitting on an engine stand in a local maintenance shop is a physical argument about the tension between innovation and absolute safety. It is a monument to a specific era of American manufacturing, a time when an engine was expected to be repaired rather than replaced, and when trust was built on cast iron and forged steel rather than software code. It proves that sometimes a machine can be so perfectly suited to its environment and so deeply embedded in a service network that the future simply cannot find a way to displace it. The rest of the world moved on. Commercial aviation embraced the high-pitched whine of the gas turbine. The American highway transitioned towards silent, battery-powered electric vehicles and highly complex, hybrid-assisted automobile engines. The sound of mechanical work was slowly engineered out of daily life, replaced by the quiet efficiency of microprocessors. But America still has a place where power remains unapologetically analog. The sky over the local airport still demands a machine that can be understood with a wrench and a feeler gauge. The market forces of regulation, liability, and infrastructure built an invisible wall around general aviation, preserving a mechanical ecosystem that the modern world is rapidly forgetting. Somewhere in an American hangar, early on a freezing Saturday morning, a massive aluminum cylinder head sits bolted to a freshly overhauled block on a heavy steel engine stand. The push rods perfectly adjusted, the spark plugs wired, waiting to be lifted onto a firewall and bring the sky back to life. See you in the next one.